Welcome everyone to the AI for Net Zero webinar series. My name is Ahmad Sheikh, and today I will be co-chairing this session with my colleague, Dr. Sarah Perez. The webinar series is a webinar series that focuses on the use of artificial intelligence in addressing net zero challenges across many themes, including energy, transport, environment, agricultural, and food system. Further, the AI for Net Zero webinar series acknowledges the critical importance of aligning AI technologies advancement with ethical and sustainable practice. Today, we welcome two early career researchers to our webinars. We will start by Tom Partridge from the University of Loughborough, and then we will have the second speaker, Dr. Misael Alpizar from Durham University. Dr. Tom is a research associate in Loughborough University, currently working on AI for Net Zero projects, which focus on remnant farming. After completing his degree in physics, Tom gained 4 years of industrial experience, where he was working on different engineering topics, including motorsports and defense. He then pursued a Master's of Science in Artificial Intelligence, where he had kind of like the foundation of his current work. Tom's work on the AI for Net Zero project combines his technical expertise with passion for sustainability, and his work focuses on leveraging AI to address key challenges in the agriculture sector. Welcome, Tom. We will share your slides. And once we get that up, the floor is yours now.
Great, thank you very much. Nice to be here today. So as mentioned, I'm going to be speaking today about ruminant farming and how we can use machine learning to try to reduce the amount of methane that is generated by cattle, particularly beef cattle, as it's a very difficult topic. I'll first talk about kind of the area around the topic, then introduce how I attempted to use machine learning to improve and understand the area, and finally the findings that we had coming out of that piece of research. This project was kind of part funded by UKRI, and it leverages the North Wake Farm platform, which is a research farm hosted by Rothamsted Research. Finally, first, a little bit about methane. It's a very potent greenhouse gas, so it has an awful lot of impact for each atom that is released into the atmosphere, approximately 40 times that of carbon dioxide over a 100-year period, which makes it very important to reduce the amount that is emitted. Furthermore, beef cattle is obviously a very vital part of human consumption, and they also release an awful lot of methane, primarily through the nose, which enables us to monitor and understand how much they produce, as well as in the rest of the supply chain, whether that be in manure management or in procurement, so delivering feed, or in any of the other many sectors. In terms of how methane contributes overall, give or take 20% of all greenhouse gas contributions are methane across the world. And that tends to be somewhat consistent across different countries as well. There's a variety of different pathways to making methane. The main ones that we're investigating here are through the diet, as I mentioned, being excreted through the mouth. These happen inside the rumen, where the cattle takes its grass that it has eaten, and it breaks it down over a reasonably long period of time in order to make energy. Moving on, so the question is, we understand that it's very important, but it's also very hard to understand the topic. There's been an amount of research in the past trying to understand, but the the issue is that methane is very hard to measure. On TV, there's a saying, don't work with children or animals. Unfortunately, the same is true in research. It's hard, firstly, to understand, to control the cattle, but it's also hard even in itself to measure the methane. So there's been a lot of work moving forwards to try to improve the way that we're gathering methane. This has been partly tackled by the Northwike research platform. They're a heavily instrumented farm in the UK. And what they do is they separate their cattle into 4 different pastures or treatment types, which allows for a very scientific control of how the methane is generated and captured. So they separate them into kind of 4 keywords. So we have green, which is quite traditional permanent pasture. They have red and blue, which is either high sugar or high sugar with white clover. White clover is known to fix the nitrogen in the soil to kind of try to help have more healthy soils. And then brown is permanently housed with intensive finishing. Which is kind of very futuristic, should we say, intensive approach designed around improving the amount of beef made per day per feed. Finally, we then use a device called green feed machine, which is a sniffer-like machine. So the cattle puts its head into a trough where it receives kind of nice sweet treats to incentivize us to go there. While the cattle is there for about 4 or 5 minutes, the device sucks air through from the base, kind of behind the cow's ears and nose, into a tube and out of the top. And then the air that passes through that device then has its methane calculated to understand how much methane extra was there compared from when the cow was there to when it wasn't, to understand how much methane the cow made either per day or, in my case, I also do some analysis to find per amount of meat that the animal generates by also adding in a weight gain component that I'll talk about later. Now, unfortunately, and this is where we get into the machine learning side of the research, unfortunately, the data sets are quite disparate. So whilst there's information about the water that is on the farm, and say the herbage or the wind or the sun or the weight of the animal, they're all very disparate data sets. So what we do is we use keys of both the time that the methane was recorded and information about where the animal was, what the animal is, so that we can say, okay, we measure some methane here and we know that the cow was there on that particular date, and we align those 2 readings together with a little bit of averaging and kind of statistics to make the data less noisy and also more trustworthy, should we say. The resultant part of that is that between November 2016 and April 2023, we gathered and processed, or I should say Northwike gathered and processed about 250,000 data samples from about 613 cattle, contributing about 5 samples per day per animal. In terms of how we process that data, and there's some of the limitations on that data, the rate, which is say the amount of methane per day, just falls out very effectively, or falls out very easily because that's directly generated. The intensity, however, is a kind of hyper feature, which we estimate by the rate, and then we say how much did the weight of the animal change per day. We also measure the weight several times during the animal's lifetime to allow us to estimate. This graph on the right shows how much shows the weight estimations of the cattle, and as well the green dots show how much methane is sensed on any particular day. So as you can see, we don't measure the methane while the animal is weaning, while it's very, very young. And we also don't measure it during the summertime because the animals are out of the sheds. Furthermore, the methane itself, the readings are very, very noisy, which makes it challenging to do both statistical and machine learning analysis, and makes it very important furthermore, to understand the uncertainties that we inherit due to that noise. Moving briefly on to a very overall methodology that we employ. It's quite a traditional methodology. So the machine learning method that we use is a gradient boosting tree regressor, very similar to random forest style regressors. It's proven, reliable, and it doesn't add too much complexity where there doesn't need to be. However, we also find that it is very effective at predicting. So we employ a variety of different models and then find that this is the most effective in our given use case. The features that we select are from a traditional correlation analysis. So we only take forward the features that either we want to know more about, for example, the breed, even if they're not necessarily that statistically relevant, or we take forward the features that are very effective, for example, the feed treatment of the animal. Finally, we explain the data using Shapley analysis, which deconstructs the model to understand how the model uses the data that's inside it to form its estimate of what the methane on any given day should be. And through that, we can understand how or what insights we can gain from the model, from the analysis, which can be used either for policy and guidance or for further research, or just to help inform farmers on how their particular environment might contribute. This shows some of the accuracy and prediction performances. So the R-squareds are quite low. Again, we believe this to be due to the high noise in the system. But nonetheless, the prediction performance is still significant enough that we can draw conclusions from the data. Moving on, we then, as I mentioned, do the Shapley analysis on the rate, and we find that per day, the weight of the animal is very, very impactful. So the way that we analyze this is that red means a high input value, which is to say, if the animal input is high, if it is heavy, then it produces a lot extra methane. And if it is low, if it is light, then it produces a lot less methane. Furthermore, we find that the feed treatment is very impactful. So in this case, it's saying that intensive feeding of animals makes more methane per day. We also find that some features are much less impactful. For example, the stabilizer crossbreed is found to be very unimpactful to the amount of methane generated. We also find that the sex of the animal is relatively unimportant. Time of day was potentially found to be very important in previous research. Our findings suggest that whilst it is important, it's not nearly so important as might be previously believed. We also find that if we look at the methane that an animal generates on any given week and use that to estimate how much deviation there should be in each week, how much randomness there is in each week, the model does a very good job of reducing the deviation of the overall sample to the kind of best case scenario. So we believe that our model, also due to this, we believe that our model is effective at predicting, given the limitations of the data set. If we now analyze the intensity using Shapley analysis, we find very similar results, but also slightly different results. The most key difference is that where before the weight was very, very important, now the age has kind of inherited a lot of its importance in the model. So now we find that very old animals tend to produce an awful lot of methane per meat generated, because their rate of growth is slowing down, but their rate of feed consumption isn't necessarily slowing down commensurate to it. We find that in this case, the relationship for intensive feeding has flipped. So now feeding intensely makes more efficient meat per methane, where before we found the opposite to be true. And many of the other kind of lower importance features remain lower importance. And similarly, we find that the amount of variation in any given week suggest that the model is predicting with reasonable effectiveness. We estimate slightly less effectiveness than for rate, but still reasonable effectiveness. Finally, moving on to the contributions, we find that real-world farming systems are complex, and much more work is needed to improve the methane sensing, particularly for beef, as it is a very, very challenging task that is very, very critical. However, machine learning and statistical analysis does help in order to start to untangle the complexities that are within this system. So it's important that we continue chipping away at all of the information that we don't have yet. Explainability tools like Shapley are similarly important in doing that. We find that machine learning has a lot of potential, but without the ability to explain its results, it's of limited value. So Shapley analysis and similar things like Line are very important in that regard. Furthermore, domain knowledge remains incredibly relevant. Without the experts to come in and say, oh, that makes sense, or oh, that doesn't make sense, the findings of the machine learning models aren't particularly useful. We still have a lot of need for domain experts to help interpret the results. In terms of the findings that we could potentially suggest from this research, we find that younger slaughter of animals may lead to improvements in the methane generated per amount of beef generated. And we similarly find that raising cattle more intensely may not generate more methane per meat generated proportionally. So that provides another opportunity for policy and for farmers to attempt to reduce the total amount of methane generated for the human requirement of the product. Finally, green feed is quite a novel technology, and it hasn't had many long-form case studies, green feed being the sensing device. And we find that even with a very, very high number of samples, the measurement noise is still a severe limitation. So further work to improve the sensing of methane from cattle is absolutely required for better conclusions from similar research. Thank you very much. I'd be very happy to take any questions.
Thank you, Tom, for the excellent presentation. A reminder for our viewers on YouTube, you need to sign in before you can ask questions. We will hold now a few questions before we move to the second speaker. I will start by my co-host, Sarah. Do you have any questions for Tom? Sarah, I think you are muted.
Sorry for that. Thank you, Tom, for the presentation. Yeah, I will have questions regarding the practicability of the implementation of your advices to farmer, especially if you're telling them that the weight of the animals is like having a big impact on the methane productions and their concerns about productivity. So did you have any experiences in or feedbacks for farmers about these policies you're advising, and do they accept them quite broadly or not? What's the insight on that?
Yeah, so I've been fortunate to talk with quite a few farmers and stakeholders representing farmers in the last few months. Unfortunately, most of the stakeholders I've spoken to represent dairy farming, which is a very different and complex area. I ought to caution that the findings here should probably not be used for dairy farming, as the long-term health of the animal and the long-term context of the animal are vastly different to that of beef farming, where beef cattle tend to be slaughtered, say 1.5 years old or so. Dairy cattle have several kind of rearing seasons, and they will be kept for quite a few years. And in particular, the cost of rearing the animal at the beginning does contribute to the overall efficiency of the animal. So I would encourage that while my findings can give a bit of context to dairy, more specific research into dairy farming is required. In regards to beef, my findings tend to support findings that are already being found. So there has been kind of consensus, should we say, that the findings are reasonable and insightful, should we say.
Yeah. And if I understood it correctly, you're showing that different crops or areas where the animals are bred, that doesn't impact that much the methane production. Am I right there?
So if I move to this one, so the different crop types are somewhat important, but not very important.
And so, does it help them for farmers? Because for me, it's quite surprising that the breeding doesn't impact like the production of methane.
Yeah, absolutely. I might offer that for breed, the breeds that are selected are all very optimized at this point. Okay. And so if, for example, we ran the experiment again using, say, a dairy cattle or using a non-optimized beef breed, we might find very different results. However, because all of the breeds that we used in this study are kind of optimized, they're more likely to find similar results to each other, and therefore the model is less likely to draw comparisons against them.
Okay. So you're saying that more variability in your data set about breeding may give you different results?
Yes, I would expect so.
Okay, cool.
Thanks, Sarah. I have a question as well while we are waiting for questions. If there's any questions coming from YouTube, in the very interesting part here is the noisy data and the measurement and the challenge of collecting real data which are relevant to help with the decision. Do you think that first question? Is the practice that the breed is all like cohort, so same age are like together, and then they are slaughtered at certain age? And can we use, this is an assumption from my side, I'm not sure if it's true or not, and can we use, if that's true, can we use that for aggregated measurements? Maybe the measurement per cattle might be noisy, but an average within a unit might be more stable or less noisy. So what do you think about that? Because you have talked to people in the field.
Agree. So my approach didn't do any aggregation of the methane sensings. There could be an opportunity for each cattle, say over a week, would generate, say, 35 aggregated samples. You could use that to make an overall aggregation, which would hopefully reduce the noise per cattle. I was quite keen to understand how methane changed per time of day, which would then prevent that aggregation. But I think that would be a valuable thing to do in the future. In terms of when the animals were slaughtered, each one is, I believe, selected once they are at a suitable condition. So whilst you'll have an entire collective kind of round of cattle, I believe that they're sent off, that they might be assessed each week, and some might be sent off 5 weeks later than the first, or whatever it is.
Yeah, and the second question is how receptive are the experts to the results, and do they kind of like you have done your homework, you build a model, you give their information. Is there any actions they are or intuitive actions they might think of it now, or are they waiting for you to close the loop and build the model and then build on top of it an optimization with decision support framework?
It's very difficult because when it comes to decisions that should be made, effective policy requires effective incentivization. And so whilst a farmer might see my research and take action in a way that should reduce methane and should not impact productivity, until the kind of systems that incentivize farmers to reduce methane catch up and verify research that is being done and continues to be done, the kind of formal incentivization, the cash in hand to farmers won't be there. So as always, it takes time for research to filter into policy and for policy to filter into behavior.
Okay. I don't see any comments coming from the live stream. Sarah, do you have any final remark or question?
No, it's all good from my side. Thank you again, Tom, for the very interesting presentation. So then if we don't have any questions from the audience, we will move to our next speakers for today. Misael Alpizar Santana is a postdoctoral research associate at Durham University in the engineering department, working on the VPP World project. His research focuses on modeling and mitigating uncertainties in energy systems caused by extreme weather conditions, particularly affecting distributed energy resources like solar photovoltaic systems. He integrates formal methods and machine learning to enhance prediction accuracy, ensure robust system performance, and reduce error sensitivity through specialized ensemble techniques. And today, Misa will give us insight into context-driven model ensembles for energy systems. So thank you very much for being with us today, and the floor is yours.
Yeah, thank you. So let me just full screen so you can see my slides. Right, so thank you. So in this presentation, I will talk about my latest research, a piece of the research that we are doing. So context-driven model ensembles for energy systems. The idea of this presentation is to walk everyone through the problem we are trying to solve, then the solution that we are proposing for the problem, and then show as well preliminary results that we have obtained from this problem. So let's start by showing this slide here. So what we are seeing on this screen on the left graph, what we see is a model used for making regression predictions, house prices, and then the one on the right is model for making predictions for movie rating. Right. So these ML models have been used in different domains, and these are examples of the applications. Now, you can see that perfect prediction would be the diagonal line, and the dots represent the predictions of the model. So you can see that there are some errors in both of the cases, right? Which is very normal. This happens very often. Is normal in models. So they produce some of the errors. Now, what is interesting to look at in these cases is, so what are the impacts of the errors that we have? Well, because maybe when we talk about house prices, the impact could be higher, but then if we talk about movie rating, we don't particularly would see a big problem in this application domain, right? Because just maybe the end user will be a bit disappointed if the movie that you suggested is not as good as they expected, right? So in this case, the impact of the errors is not something super relevant. But now, if we move and apply these regression models to something different, to another domain, such as making predictions of renewable energy generation, then the thing changes slightly, right? So in this case, what we see is in this graph, the green line represents the actual generation of energy, and then the dotted orange line represents forecast prediction. And this comes from a real example. This happened solar forecast error in Germany. So we can see a 20% gap difference between the prediction and the real generation. And so what was the consequence of this error? That the prices of the energy were 10 times the original price. Why this happened? Well, because everyone rushed to make bids to get the energy that they needed for their own applications. So if we move into looking at what are the specifics errors that we may encounter due to forecast mispredictions, and how this impacts or has consequences in the real world. So we have this graph obtained from a paper that I found very interesting, that is kind of describes the problems that we can encounter. So the forecast errors: for overestimation, you can get shortfall in supply, prices spikes, such as the one that we saw in the previous example, emergency action. For the underestimation, you can get overcommitment of backup, unnecessary fossil dispatch, missed storage. So as you can see, when we move into a real domain, the impacts could be different. And I guess the key message that I am trying to give is, there are some domains where the errors that we make, or that the models that we train make, are not super important, but there are domains where the errors that happen due to our model could have significant impact in the real world. And then there is something that we would like to do about it, right? So the traditional way in which we assess or we evaluate the models that we have trained is using these 3 metrics. There might be some others, but this is like very common. We use mean square error, root mean square error, coefficient of determination. Basically, the first two are giving us an idea of the magnitude of the errors that our model is doing. So the larger the value, the larger the error, the worse is the model. And then for the R2 coefficient, is a value between 0 and 1, when 1 represents a perfect model and 0 represents obviously a model that is rubbish, is not working, right? So the higher the R2 is, the better the model. So in this case, the metrics that have been used for evaluating the models are very informative, are very important, but we argue this is not enough, right? Because as we saw previously, there are cases where the errors have different impacts, and these metrics are not informing or giving any idea of the type of errors that the model is making. From the point of view of these metrics, 2 models, right? One that makes less of the type of error that you're more concerned with, compared with other that makes more errors for the type of errors that you are concerned with, are not different, right? As long as the performance metrics are similar, which is the case very often. Now, this is what happens when we evaluate a model that has been trained, and what happens during the training of the model. During the training of the model, we use something called the loss function. So the idea of the loss function is to have a way of measuring the error between the prediction and the ground truth value. Yeah, so during training, we want to reduce this error as much as possible, so the neural network will learn how to tweak the values to adjust so that the prediction is closer to the ground truth value. Now, the very common, very famous loss function, mean square error, is this equation that you are seeing on the screen without this red part. So this is the MSE loss function, the traditional one. Yeah. So as we said, also during the training of the models, the training of the neural network is trying to decrease the errors as much as possible, but is not looking into the direction of the errors. Something similar to what we said previously. During training, both type of errors are as eagerly avoided, so it's not paying attention. It doesn't care what is the type of error that you might be interested in. So we proposed adding this circle part here in the loss function. And now with the introduction of this part in the equation, what we would like to achieve is to give to the model an idea of the direction of the errors. And then based on the direction of the errors, which are the type of errors that you would like to mitigate, we give a penalization value, which is this W here in the equation. So the intuition is that by making the loss error larger, you will end up with your neural network realizing that by decreasing because the idea is, the objective is to reduce the loss as much as possible, right? So by making a reduction of the loss during the training of the neural network, you will also be making a decrease in the total number of misclassifications of the type of the problem that was selected. So if you said overestimations or underestimations, sorry, are more important, then you choose one of those, you penalize them, and then you make an evaluation of the results. So that's the intuition, right? And so we actually implemented this and then run some of the experiments, and I can show you an example of the things that of the results that we obtained. So what you see on this slide here, so let's focus first on the top left graph, right? And specifically, sorry, on the left graph. So what you are seeing here are different models. So the blue dots represent the baseline models. So this is what we obtain when we train using this traditional MSE loss function. And then the rest of the markers on the graph, this yellow, green, and red, represent the models that have been penalized. So where we have used the new term that we introduced in the loss function. So as you can see, as the penalization value grows, we are seeing a decrease in the number of underestimations. So in this case, we regarded underestimations to be more important. So we wanted to mitigate underestimations during the training of our model. And we can see that the penalization is effectively working. Now, a second interesting thing that we can observe in this graph is that as the penalization grows, we see a reduction of the underestimations, but we also see that the R2, so the ability of the model to describe the variance of the data, is decreasing as well, right? And then we say, let's pay attention then what happens on the other direction. So what are the consequences of adding this penalization into our models? And then what happens is what we see on the right part. So now we are seeing that overestimations grow, right? And then if we pay attention to the metrics such as RMSC or the R2, so we now move into the bottom right graph here, we can see that as the penalization value grows, the error grows larger as well. And what we previously observed, the R2 score is consistently declining as we increase the penalization value. So this is telling us that our technique of applying penalization to the type of error that you want to mitigate is working, but it comes at a cost, right? So what is the cost? The cost is that we are increasing the error on the other direction, which is suggesting a trade-off. Now, this means that we need to find a way to equilibrate this, right? So if we wanted to get the best of the baseline models combined with models that have been trained to tackle a specific concern, then we should find a way to meaningfully combining all of them so that we obtain better predictions. And this is where Ensembles comes into this part of the work. So the definition of ensemble is, I think it comes from something called the wisdom of the crowd, which assumes that if you are in a room with a lot of people and then you ask a question, usually the most voted answer is the correct one. So the idea of the ensemble is that you will have a group of models instead of a single model, and then you will ask questions to the group of models, and then you hope that the answer or the result of consulting an ensemble is better than using a single model. And it introduces the idea as well of specialists and generalist models. And I guess the best analogy that we can use is imagine a room full with different doctors, different specialists. So you will have a GP, you also have a cardiologist, ophthalmologist, oncologist, and so on. So if you want to ask a question about a disease, say you ask a question related to heart disease, then you will obviously pay more attention to what the cardiologist has to say, right? So something similar happens in this case. When we create an ensemble, we combine our baseline models, which are the models that have been traditionally trained, with models that have been trained to specialize in specific types of errors. And then by combining these models, you're hoping that the model that you train will learn how and where to use each of the models depending on the regions of the data that you are considering or giving as an input to our model. So this is what we did in this part of the work. We created an ensemble using a neural network. We created a meta model to further train using a set of models from the ones that we have trained in the previous example. And then, so I can very quickly go through an example of the results that we obtained, right? So this, what we see on the left part, so we have 30 of the baseline models. Yeah, we created the ensemble, and then the results of combining these models and synthesizing the ensemble is the red star that you can see here. So what we are seeing is that by combining all these individual models into an ensemble, we have decreased effectively the total number of underestimations, but we keep a competitive R2 score. So actually we have improved it, right? So this is expected in ensembles. When you combine a set of models, you would expect the performance to be improved, which means that our meta model is working as we would expect. And we are getting rid of the problem of decreasing the performance of the models, but still keeping a competitive R2 score. So this is the problem that we saw in this case, right? So as we increase the penalization, we saw a reduction in the number of underestimations, but we also saw degradation of the performance of the model. And when we applied our ensemble, this changes, right? Now, if we move on to the right side, in this case, we synthesize an ensemble that combines the baseline models with penalized models. So in this case, we choose only 3 of the penalized models. And what we can observe is a further decrease in the total number of underestimations that our model is making, and also keeping the competitive performance. So we think that applying our ideas and applying the pipeline that we propose in this work is helpful, and it helps us to, number one, identify the type of errors that are more impactful in the domain where you are expecting to deploy the models. And obviously, this needs to be done carefully, using advice from experts' domains. And then the second thing is, once you have identified the problems, you can mitigate them by using our technique of penalizing the type of error that is more concerning for your application. And then the third contribution of our work which is you use the meta model ensemble that we propose that combines the baseline models with the context-aware models, and then we synthesize an ensemble that is effective in making a reduction in the number of errors, so number of concerns that you are that you want to mitigate, and keeping a competitive performance of the models. And this is the end of my presentation. So I'm happy to take any questions you may have.
Thank you very much, Misa, for the very pedagogical presentation. It was very clear and didactic. So I think we will start with questions from the studio here. I have several of them. So I'm wondering, when you set up your loss function with your indicator function C, which seems to constrain your misclassified area in ensembles, right? So is this an iterative process, and do you adaptively evaluate this function, or is it fixed at once at the beginning of your training? And if it's adaptively evaluated, on which criterion, and is it based on mean square error or something else?
So you mean, sorry, let me move. So you are seeing this slide, right, with the one with the MSE. Yeah, so what you mean is, so yeah, this is an iterative process, but this happens naturally during the training of the neural network, right? So the neural network will apply this at epochs, different epochs of the data. It will be passing the data over and over during the training, and then the loss function will be calculating the error. So then the neural network back propagates the errors and it tweaks the weights so that the loss function is reduced and you obtain a closer value to the prediction. Mm-hmm. So that is on that sense, that is an iterative process itself. So what we did is by proposing a modification of the loss function by adding in this way is, number one, we want to identify, obviously this part of modifying the loss function happens once you have trained your baseline models, right? So you first train your baseline models, which is the traditional models, such as the ones that we see in this slide, the blue dots. You train the traditional models, and then once you have trained your traditional models, and you investigate, and with experts domains, you realize what is the type of errors that is more impactful on your domain. Based on that, you decide if you penalize, for instance, overestimations or underestimations, and then you train your models based on that information using the penalization weight.
So you mean that your indicator function is set up at the beginning of your training then, and doesn't change along the training at all? So you don't adjust it on the fly, right?
No. Yeah, so you set it at the beginning, and then you train the models with this value, and then you analyze the results that you obtain.
Okay. But okay. And why don't you adjust it on the fly? Maybe like would be like
adjusting on the fly. So but what do you mean adjusting on the fly? So changing the penalization value, giving sometimes, I think that would be probably wrecking the training of the model. So we use a fixed value, so to be consistent, because if you start giving different values, you will end up with so during the training of the model, I think you will be wrecking what we will obtain at the end will probably be rubbish, because you're just giving values during the training, so the loss function won't know exactly which part of the region of the data to identify and to tackle, because it will be adjusting in a way, and then you change the weight again, so the error looks larger again. So the neural network, from the neural network's perspective, it will be, so the adjustment I did is rubbish, I need to readjust again, and it will be like very noisy training.
Yeah, you will. Yeah, okay.
Yeah, I'm guessing that would happen, because I haven't played with it, but definitely that sounds like.
Because I'm just thinking about, like, for me, it looks very similar to focal loss with cross entropy, but then on focal loss.
I think cross entropy is used for a different type of problem, right?
Yeah. But in this case, you're adjusting your focal or your focus on a misspecified area in a classification problem, but based on the gross entropy itself. So
yeah, I don't have all the information for the other, but just by the way, I have performed a similar idea on object detection and image classification, which uses cross entropy. So I think in that domain, the weighting the loss function in a similar way is usually used when you have imbalanced data. So this technique is not something completely new, right? It's just the shift in how you use the technique of modifying the loss function and the ways in which you will use it.
Just to elaborate here, Sarah is mentioning a specific kind of loss called focal loss, introduced by a research group in, I think it was Facebook a few years ago, which is worth looking at. They do adjust the weight to focus on misclassified samples. And I agree with you as well that changing the loss function along the way is risky, and it just comes back to learning the loss function in a context of GAN, generative adversarial network, and it's min-max problem. So you need to slow the training. It creates issues. But I want to go and step back. If we are interested in a decision, the community which works on decision making are the reinforcement learning community, by meaning they don't train to match their data, they train to take optimal decisions. And in that community, everybody was saying, okay, let's train a model and then optimize on top of that model the decision. Then they discovered something called objective mismatch, which is that if you optimize your model to be mean square optimal, maybe it's not the best model to take the decision. So they gave up on the model and they did a model-based reinforcement learning. What you are trying to do now is somehow human in the middle, and by meaning let's analyze our errors and think about it and maybe provide an explainable way to how do we adjust our loss to eliminate the objective mismatch. Mean square loss is not optimal for your objective, either because there's downside risk and underestimation or overestimation. So in your mind, when you did that decision, what was the objectives which lead to that? You touched on that, on the impact, but what was the objective? Is it energy storage or energy kind of security? You don't want to undersupply the system.
Okay, yeah. So just to forgive a little bit of my background, so I am a computer science background. I'm not energy background. So I entered this project, bringing like my ideas from computer science world. So actually, this part of the work that I just presented came as a side part of a project that I was working on, how to mitigate the impact of the adverse weather conditions on distributed energy resources, and we happen to need a model for making predictions so that we can analyze the trends and probably inform proactively to make decisions. So how do you do this? By using a predictive model, right? So we go use prediction. So what type of predictions do they use in this domain? Okay, so common models could be long short-term memory models, and I started playing with them for a little bit for making a renewable energy generation prediction of solar panels. And then while I was playing with these models, I realized the errors that they were making were similar. So when I did my PhD, as I mentioned previously, I was working on image detection and object classification, and I applied this idea of having error reduction by changing the loss function. So I think for this domain and in this application, this idea could be relevant as well. And then by reading a little bit, I also realized that in fact, there are errors that have some type of errors, such as overestimations or underestimations, depending on the context of what you want to do in energy prediction, have different impacts. And so stakeholders may be interested in applying this idea for making the reduction of the errors in the area where they think this type of errors is more impactful. And so I think that I didn't have like a specific example in mind. It was just like realizing that this could be helpful because the errors indeed have different types of impact. Some errors are more tolerable than others depending on the context, such as the example that we saw previously, right, from the real world, that in Germany they predicted more generation when in fact they produced less generation, and this created a big problem. I think without like something specific in mind, but kind of looking at high level of the things that could happen. So probably there are many applications or other domains that I'm not very aware of that could help with. But I think that in general, the idea is that you now will be aware of the type of errors in your models, and you will have a mechanism to do something about it.
Thank you for sharing with us the story behind research. And it's a non-linear path of doing research, where you start with something and you leverage your background, and you introduce something new. Your team, you'll find it interesting, and so forth, so on. Sarah, do you have any final questions for Misa?
I mean, he answered like my second question already, so it's good for me.
I would like to ask one more question about the ensembling techniques. I kind of like missed the details. Are you doing stacking where you weight the models differently based on cross-validated data, or are you just using equal weighted system, or?
No. So it's applying a neural network as well. So it's a meta model. So it's a neural network that trains the models. Because I tried genetic algorithms first, but I had a problem because genetic algorithms was trying to solve the problem linearly, and I wasn't able to defeat the best model using genetic algorithms. So I changed to something more dynamic. So I think we needed to give different weights for the models in different regions of the data, because the baseline models are good for some regions of the data, worst at the others, and then the opposite happens with the penalized models. And so I ended up working with a neural network that has been trained using these models, and this is how I obtained the results that look more as what we wanted to see, because previously with the genetic algorithm it wasn't working as expected.
Fair enough. Thank you, Misa, for answering all our questions and for the excellent talk. I will remove the session. I will add our first speaker. And now I would like to thank again our speaker, Tom and Misa, and my co-host, Sarah. And I would like to announce the next webinar. As a reminder, we have switched from a weekly webinar to a monthly webinar. The webinar is the first Tuesday of each month, and it's at 2 p.m. It's now British summer time, because the time have changed in the UK last weekend. And we are pleased to announce our next speaker, Professor Elaine Spiller from Marquette University, our first speaker from across the continent, the US. And the webinar is scheduled on the 6th of May at 2 p.m. Thanks again for joining us, and for those who will watch us in the future, thanks to our speakers and to the co-host, and we look forward to see you next time. Goodbye.
Thank you.
Thank you very much.